Here we go. Okay. Inductors. So self-inductance versus mutual inductance. So self-inductance, you have a coil of wire, solenoid, and if you have a changing, this is kind of what we were going over yesterday. Um, say the current is increasing. Okay. What happens is that produces a flux going this way. Okay. Change in flux. So there's um, an electric field that goes in opposition to that goes this way. If you notice, this is in the opposite direction of current flowing through that solenoid. Does that make sense? Okay. And it fights it. Okay. So this is like a layer deeper understanding of like what's going on inside a solenoid. We've never really talked about it. All we've talked about is, hey, it produces a magnetic field. But what happens when you try to change the current? The solenoid fights it. Okay. Um, we can say, you know how in a capacitor we said that stored energy in an electric field? An inductor stores energy in a magnetic field. Okay. The role that an inductor plays in a circuit, it acts like inertia for for a current. So if you try to change the current, the inductor is going to fight you. Whether that's increasing or decreasing is like, hey, let's keep doing what we were doing. Like it's not going to win, but it's going to fight you. Just like inertia is never going to win, but it's going to fight you in terms of a change in motion. Does that make sense? Okay. So inductance is kind of like capacitance, but for an inductor. And what that says, so capacitance is how big the bucket is for a capacitor. Inductance is how much inertia it has. Okay? And the inductance is given by the ratio of how much flux there is in this solenoid. Okay, so like magnetic field times the area divided by the current. Okay, it's that ratio of how much flux there is for a given amount of current. That ratio. Okay, I have Tesla per amps. Sorry. Webers, not Teslas. Teslas times meter squared. Webers per amp. Okay, so flux is in Webers. Inductance, we give a unit called a Henry. Okay, which is a Weber times an amp. Getting kind of deep in here in terms of units. Okay. If you look at the magnetic field of a solenoid, that's equal to permeability of free space times the number of loops over the length times current. And flux is equal to area times the magnetic field. That magnetic field is here. Substitute that, all that stuff into here. The current gets canceled, and you've got in, oh, yes. So that's your flux is number of loops, number of loops times the area times magnetic field. Good with that? Can't read that, I know. So this is number of loops times the area times your magnetic field. Charlie.
In the units, did you say that A is also area? Or is
No,
this
is amps. Because, so you've got Webers per amp. Okay. Just like a resistor, resistance is equal to voltage over current. That's measurable in a circuit. We can measure that stuff. So that's like experimental. But there's geometry with resistivity times length over area. That's how you'd find resistance from the geometry. Okay. Capacitance is charge per volt. But you can find that with, never know. Come on. Area increases. D. I think epsilon naught goes below, maybe. I don't know. Never remember where that guy goes. That one. But that's the geometry. It's the area of the plate over the gap distance. Capacitance. This is experimental. Okay. You have magnetic, this is the flux over the current, but this is the geometry for an inductor. Okay. So your number of loops squared, so that's like a huge thing. The area, so like the cross-sectional area matters for an inductance over the length of that solenoid. Good with that? They, on the equation sheet, give you interesting. Wild. Memorize this. They give you this, but they don't give you that. Okay, memorize that. Huh. That is crazy. Yeah. Have that one in your back pocket. All right. That's the schematic symbol for an inductor. Okay. Solenoid.
Inductor, like, always in a solenoid?
No. But in this level, yes. Okay. How are we doing so far? Just kind of. Okay. So here are, this is more real world stuff. This is not on the AP. So here you could get a whole assortment of inductors. You get these from India. Okay. So here, this is the permeability of an iron core is like whatever substance they put in here. So you can change the inductance by adding a iron core. Okay, and so here you see some that are air filled. Here you see some that are like have iron in the middle of them. Okay, if you pull out a circuit board of like a big, you'll find some of these. Okay, go to that. You don't need to know that. That's just, okay, it's like adding a dielectric to a capacitor. Okay, so how these play out in a circuit. So it works just like a resistor. So in series, you just add them up. In parallel, you do the 1 over. Okay. So if you're adding them up in series, it's kind of like making the area bigger. Okay. If you add them up in parallel, it's like adding their lengths together. Okay. This is going to cause the inductance to increase. This is going to cause the inductance to decrease. Here's that. I've yet to see that on an AP, but you know, I'm just getting you ready for anything and everything. Get to that. So resistors, inductors, same math. Oh, shoot. I'm gonna come back to those. All right. Reminded me to come back to those. All right. The induced voltage. Actually, I know I'm not gonna remember that. You aren't either. Let's pull these. I think I shoved that down here. Let's do this. All right. So you got Faraday's law. Okay. I'm just going to look at the magnitude. Okay. So the rate at which flux is changing times the number of loops. Okay. So the voltage across a solenoid, the area is not going to change. You got the number of loops. So it's the rate at which the magnetic field in the solenoid is changing. Okay. So this is our equation for the magnetic field in a solenoid. Okay. So permittivity of free space, it doesn't change. The number of loops doesn't change. The length doesn't change. What does change is the current. So for the voltage across an inductor, it's all of this. Okay. Times the time derivative, the rate of change of current. Okay. This all gets clumped together in inductance. Good with that? So this is the takeaway, and that I really hope is on there. Wow. There it is. All right, good. Yes. They write it like this on the equation sheet. The negative comes from Lenz's law. It's fighting that. You can go hardcore. I'll teach you how to deal with the negative. Personally, I ignore the negative, figure out what it does conceptually, and then figure out from there. But mathematically, you can do it this way. Okay? But that and that, same thing. Okay? So what this is doing, I'll walk us through this again. Okay? So here, let's say, so you have current going through it, creates a magnetic field going up. Okay? Let's say we're increasing the current. Okay? So the change in flux is going this way. So the electric field, or the magnetic field that's induced is in opposition to that. And it's going to go, the electric field that's induced is going in opposition to that. So you have, this thing is fighting that increase of current. Okay. And so because of that, there's a voltage drop across there. And how quickly that current is changing determines how much voltage is induced across that. Okay, good.
And then that induced magnetic field, it's going to make it counteracting current.
Correct.
So the overall current is going to decrease.
Yep.
Okay.
Yep. Okay. So this is, we'll get into the weeds here in a little bit, but this is where voltage comes from. Where there's a voltage drop or a gain depending on what you're trying to do with the inductor as you change the current. Okay. But it's equal to this. The inductance times how quickly you're changing your current. Okay. All right. So this is dealing with the math of this. Okay. So if we are increasing current, then you got flux going this way. The change in flux is this way. We're in opposition to that. Okay. So what this does is creates an electric field going this way. And so this becomes, as current goes through here, this becomes a voltage drop. Okay, you're starting higher electric potential, and you're going to a lower electric potential. So this kind of behaves like a resistor. You have a voltage drop across this. Okay. If you are okay, so you would be increasing your you'd have a positive change, positive derivative of current, and that negative sign means you're going to have a voltage drop. Okay. If you're decreasing current, so let's say, let's see what my next slide. If we're decreasing current, okay, so we've got current going, why do we do that? Current going this way. Shoot. That's not how I draw it. Frustration. Okay. Sorry. This is looking at the induced magnetic field, not the magnetic field. Frustration. Okay. Forget the diagrams. Okay. If you're decreasing your if you're decreasing your current, then the induced electric field wants to keep pushing the current forward. It's like, come on, let's keep doing what we're doing. Like, don't change it, keep going forward. And this becomes, if this is negative, there's a negative in the equation, this becomes a voltage gain. This acts like a temporary battery. Similar to a charged capacitor, it has a voltage gain. Does that make sense? Okay, it's like, come on, let's keep going. All right, so here's, this is the math. Okay, so if we have direction of current, this is a voltage drop across the resistor, where this is our comfort zone right here. Okay, we have a voltage drop. Okay, if current is constant, this behaves like a wire. Okay, and if it's ideal, there's no resistance in that, and so the voltage drop, there is no voltage drop or gain across that. If current is constant, acts like a wire. If current is increasing, this acts like a voltage drop, just like a resistor. It's a higher electric potential, this is a lower electric potential. It's fighting against that. If current is decreasing, then this becomes a voltage gain as we go this way. This has a higher electric potential over here, and it acts like a temporary battery. Okay, Charlie.
Is delta V then always negative?
No. This is positive. So
the current's decreasing, the derivative is negative.
Right. This would be negative, and then there's a negative sign in this equation that makes it plus. You right with that? Like.
Then why would they differentiate this negative and positive in these two cases?
They did the math already. And no, that's like them summarizing. You did one of those already. Is this lunch period or is this? I don't. You can tell. Okay. All right. So give that one a shot. Tell your neighbor.
I think it's all the above. If it goes A and B. C. It can be two things at once. Schrodinger's cat.
Oh, wait, no.
And then.
I think the point of Schrodinger's cat is that yeah, he was trying to say it was stupid. I was just smiling.
What?
Schrodinger's cat, he was trying to say that Schrodinger's cat is like the lowest form of observation that you get after spending like 3 months in a quantum schools.
Okay. Correct answer is A. Okay. This has a higher. This becomes like a battery. There's a voltage gain as we go this way. So this has a higher electric potential than that. More energy. Good? Okay. Oh, you don't know that one either. Okay. We'll get to energy here in a second. I feel like I should give you equations.
Oh wait, they. 2 out of 2 12. Yeah. No, it's yeah. Yeah, I was gonna say yeah. It's A inverse. No. Dude, I looked at it test last night. Like just I know they do the other. It was like great. Yeah, a lot of the questions on graded though were like damn. What man is the inverse of A transpose plus 2007 times C?
Correct answer is
Multiracious buffaloes.
correct answer is B. Okay. This has, let's see, conceptually I'm trying to like, this has okay, we can do the math here. Like just take this ratio of voltage over inductance. But this has less inertia, yet there's a greater voltage drop across that, which require a whole lot more change in current to produce that voltage drop than this that has more inertia, yet it has less voltage drop across that. Yes, no. Okay. All right. So this idea that energy is stored in a magnetic field. Okay. This is the similar thing to the energy stored in an electric field with capacitor. Okay. So power is equal to current times voltage. Okay. And power is just the rate of change of energy. Okay. And voltage of an inductor is L times derivative of the current. So what we're going to do is take the integral of both sides, and we're going to do this as a function of current on this side. Okay, over here it was as a function of time, going from 0 to t dt. Okay. And here we're going from, we're assuming we're starting at 0 current, so we're just turning it on, and we're going to some current. Okay. And so when we integrate that, we just get 1/2 Li squared, and that is on the equation sheet, just like that. Yeah, it's definitely possible. Do that. Actually, you know what they do? Scratch that DT. They do this. DU. They knock out DT. You're probably screaming at me for people, math people. That's what they do. Is that a thing? You can just knock out DTs?
It works. That's why we have the notation.
Yeah. Good at that.
If we integrated with respect to t, you can't solve it.
Right. So it's like a double integral. Yeah, which we're not going to touch. Okay. So energy density. This is how much energy there is per area or per volume. I've never seen this. There's like energy density of a capacitor as well. It's like how much energy is stored in the electric field per volume. It's a thing, but I've never seen it surface. It's not on learning objectives. So just throwing that out there. Okay. All right. Twice as many turns. It's twice as long. That's thumbs up when you have a guess. Have a conversation.
So number of turns is twice as much, squared is 4. Diameter is twice as much, so radius is twice as much. Squared
The cool party just stood a chance against the arena house of the election.
Correct answer is I got C. How about you? Okay. So this is 4 double squared. The diameter make R squared to find the area, so that's 4, and then L is length, or the length is doubled, so 16 over 2. 8. Good. Thumbs up when you have a guess. Have a conversation.
Oh. So it's
Correct answer is E. What is it? 1. Okay, so this has no impact on the magnetic field, but it does have impact on the inductance and therefore how much energy can be stored. Good with that? Correct answer is C. Good? Okay. I think we can do it. Here we go.
Did we end up with a like CLR? RCL?
What?
Did we end up with an RCL?
Uh-huh.
Oh,
Okay, RL circuit. You have a resistor and an inductor. We already used I for current. Okay, so what you have is initially we're going to look at a okay, so we got a battery. It's hooked up. We got current going this way. Okay, and then we're going to switch that from A to B. Okay, so we're going to disconnect the battery. Okay, and so what does this inductor want to do once we disconnect the battery? It wants to keep things going. Acts like a temporary battery. You have a voltage gain across this. It's like, no, keep on going. We don't want to stop this. Okay? Does that make sense? And we have a similar, oh dear. We have a similar relationship of what we had with an RC circuit that's being discharged. A capacitor and a resistor. Okay, so initially it's like, come on, let's go, and it keeps on going, and it obeys the same mathematical relationship of exponential decay. Our time constant is L over R instead of RC. Okay, if we think about that as the inductance goes up, that's more inertia saying, come on, keep going, and it takes longer. There's a larger time constant. But if the resistance is bigger, that slows things down faster. In an LR circuit. In an LC circuit, no, sorry, in a RC circuit, the resistance gets in the way of the charge going from the positive plate to the negative plate, and that increases the resistance. Sorry, that increases the time constant for an RC circuit. But an RL circuit, it makes it drop quicker. That makes sense? Okay, I'm kind of showing you the end result first. Okay, we're going to go back through this. All right, so this is the conceptual. Okay, I like looking at it like this. Here's the magnitude of it. Okay, and if the current is increasing, it's a voltage drop. If the current is decreasing, it's a voltage gain. That's how I like looking at it. Like I don't mess with the negative sign that's in the equation. I just drop it. Okay? But if you want to do the math approach, okay, this is the way they give it to you on the equation sheet. They write it like this. That's how they write it, like this. Okay? If your current is increasing, you have a positive derivative of current. That negative sign is there, so it's a negative, so it's a voltage drop. If you're decreasing current, then that's a negative change. That negatives cancel out and you get a positive. So I don't care how you do it. Just pick one or the other. Don't do both. Okay? So, Kirchhoff's loop rule after it's been switched from A to B. Okay? So, you have a voltage gain across the inductor, and there is a voltage drop across the resistor. Good with that? Okay. So this is L d I dt minus, I'm going to put, can I put a lowercase I? And this is a lowercase r. Good with that. Going to make them equal to each other. Okay. And I'm going to bring R over L dt, doing separation of variables. Over here, I've got 1 over lowercase I di. Right with that. See where we're going here? We're going from time 0 to time. Here, we're starting with your original current, because there's current initially, and we're going to some Yeah. Go to some less than our original. We're decreasing the current. Okay. So you got a natural log of I over I naught equals to R over L. I feel like there's a negative. Where's my negative?
Should it be RLT? It's disintegrating.
Yep, it should. Where's my negative? Natural log, final minus initial. Where's my negative sign? We're decreasing. That makes that positive. Doggone it. Yeah, but the current is decreasing. So that there's a negative. Simon. Stop. LR sentence.
Is it from changing voltage to negative Li?
I hate this. Dumb. Okay, I get it. All right, so this is the negative sign is part of the equation. When we go from our original maximum to something lower, that's what makes this quantity negative. All right. See you.
Let's see what it looks like when I get a call from Seth.
Restoration.